Hi everyone, I'm Guido Giachetti, currently a PhD student in SISSA Trieste, and today I'm going to present my work about the two-dimensional XY model in presence of long-range interaction. Now, why is this model interesting? To understand this, let us resort to the standard Hamiltonian for a generic ON model in presence of long-range interaction. As you see, there is this ON coupling weighted with this power law coupling, which represents the long-range interaction. And you see D is the dimension of the system, while sigma is a parameter which measures how much long range we have basically, and is a positive parameter in order for the Hamiltonian to be extensive. Now, the common law about this ON model, ferromagnetic ON model, is that we have order and disorder phase, just like in the short range case, but that the critical exponent, the universal quantities at the critical point, can be influenced by sigma. In particular, this happens within the so-called SAC criterion when sigma is less than this critical value 2 minus eta short range, where eta short range is nothing but the anomalous dimension of the short range phase, which corresponds to sigma equal to infinity. Then, when sigma is greater than this value, we basically don't see any change in the universal quantities at the critical point, while this happens in this other region. This picture is somehow challenged by the XY model, in which we wrote this scalar product as the cosine between this when theta is the angle of the corresponding angle of the rotor. The picture, as I was saying, is challenged because basically we don't have a single fixed point in the short range, but rather a line of fixed points. So it's not clear whose eta short range. There is no a temperature independent eta short range, and all these SAC criterions stuff does not apply trivially. Now, to understand what we have done, let us revise briefly what happens in the short range case. The short range, let us consider this Hamiltonian in which the interaction is restricted only to the nearest neighbor, and let us consider the low temperature phase. In the low temperature phase, only the long wavelength spin waves are relevant, let's say, and so this in this Hamiltonian, this difference here is always small. Now, what we can do then is to expand at low temperature this cosine in Taylor, and we end up with a quadratic theory, a Gaussian theory massless, which describes this theta. In turn, this tells us that the power law of this Gaussian theory are basically always the correlation functions, of this Gaussian theory are always power laws, as we can see. And there is this peculiar fact that this exponent here, which we will refer to as eta short range, actually depends on the temperature. Now, this picture, however, is not considering that theta is not a real field, but a phase. And since it's a phase, we have this configuration, like the one on the right, which are topological. Let's see, in other words, we have put vortices in this point, and then if we compute the increase of this angle theta on a closed path within circles, this point, we see that the variation of theta is not zero, but rather is a multiple of 2 pi. This is possible only if theta is a phase, and this feature is not captured by the simple Gaussian theory. Kosterlitz Thouless basically shown with a renormalization group argument that these vortices, or rather the vortex pairs, are relevant only at high temperature, and in particular they become relevant as soon as this eta, this parameter eta here, which is the anomalous dimension, let's say the temperature dependent anomalous dimension, it becomes greater than 1/4, so that only the fixed points with eta less than 1/4 are actually stable under this topological excitation. Now, what happens instead in the long range? Let us imagine that we start from our short range theory, and we introduce a small long range perturbation when G is the perturbation parameter is assumed to be small. Here, as you see, all the pairs all the pairs of the lattice sites are present in the Hamiltonian, and they are weighted with a slowly decreasing power law kernel. So it's not immediate that we can actually perform the same approximation and replace the cosine with a quadratic term. In fact, if we do all things carefully and we don't assume anything, we end up with this very peculiar continuous limit in which there are both non-locality, that is basically encoded in this fractional derivative here, and but it is intrinsically interacting, as you see, because we couldn't expand the cosine and the sine in this action. Now, if we consider the dimension of this perturbation on top of the Gaussian short-range theory, we see that its dimension is sigma plus eta short-range, where eta short-range is the exponent of the correlation of the short-range theory. Now we have our rough picture, but still convincing. That is that the Gaussian fixed point line is destroyed when eta is large and then when the temperature is high by vortices, and is destroyed instead by long range perturbation when temperature is low, and then this eta is less than 2 minus sigma. That is when this long range perturbation is relevant. Now, our analysis tells us that there is a chance for the BKT transition to survive as long as sigma is in between 7/4, that is 2 minus 1/4, and 2. This is confirmed by a more careful analysis, a more careful renormalization group analysis. In fact, if we do a perturbative renormalization group in G, we see we have this picture. This is the J plane, and we here we don't consider vortices. We switch off the presence of a topological excitation, and we see that we have this ball line that separates the green area in which the G goes to infinity and the long range is relevant, and these are other in this blue area in which G goes to 0, and we end up in the short range fixed point area. This is nothing but the BKT phase, while this one is the ordered phase, in which we expect a non-zero ordered parameter. Let us notice, however, that closer to the origin, the lines end up on the left of this dotted gray line. This means that when we switch on the topological perturbation, basically those points become unstable, and the flow basically escapes, run out in the third direction, in the third dimension, and vortices destroy the order. Now, if we take a generic physical starting point of the RG flow, that is the dotted red line, we see that for low temperature we are in the order phase, for intermediate temperature in the quasi long range order phase, and then when there goes also a BKT transition, and there is also a high temperature phase. Now, this is true as long as sigma is between 7/4 and 2, because if sigma were less than 7/4, basically this second line becomes start to be on the right of this other line, and basically the whole BKT phase, the blue one, is swallowed by these two instabilities. Now, the new low temperature phase has some very strange feature. In fact, as you have seen in this phase, G, the perturbation parameter, goes to 0, and this says that our analysis should be perturbative analysis should be hopeless. But at the same time, one can also see that J goes to infinity. That means that the anomalous dimension goes to 0. Now, since in this theory, in this region, the theory has no anomalous dimension, we can, however, say that this theory is Gaussian, and this is the only candidate, the only acceptable candidate that we have that has the right features. For example, it's non-local, and this in turn tells us that this Gaussian field theory can allow for a finite magnetization because Mermin-Wagner theorem hypothesis don't hold, basically. And in fact, if we do things carefully, we see that we have this very strange behavior on the magnetization. The order parameter goes to 0, but with all the any order derivative are 0, so that basically although the m versus t curve is not analytic, we have a very smooth transition. Now, to conclude, this is our final picture. Basically, we have for sigma greater than 2 only the BKT phase, which separates the quasi-Longrange order and the disordered one. For sigma less than 2 only the spontaneous symmetry breaking transition, which separates the ordered and disordered one, while between 7/4 and 2 we have this blue transition, which is our and basically this means that we have 2 phase transitions and 3 phases. The blue transition is the infinite order one, while the nature, the details of this spontaneous symmetry rating for sigma less than 4 is not predicted by our model, since our starting point is the Gaussian short range theory is no longer a good starting point in this region. Now, thank you for your attention, and thanks to my collaborator that you can see here that made this work actually possible.